I'm Anil Kumar. I've developed this series for my student Anna, who wants to understand all about derivatives. So we'll have 6 sections in this particular series. In 2.1, we'll just see differentiability, and we'll also see how to find derivatives using tangent lines and first principle. So we are going to discuss questions like this. For example, identify the points where the functions are not differentiable, and we'll have a couple of graphs, right? So you have to identify points where the functions are not differentiable. At any stage, you should actually pause the video, copy the questions, try them out, and then move forward. Then we'll take up this kind of a question, which says find the slope of tangent line to all these curves are actually for function y equals to x to the power of n, right? So the point 1, 1, which I'm going to mark here, is the point of our interest. So what you have to do in this particular exercise is that you have to copy this graph and then draw a tangent line. Once you draw a tangent line, you can find slope of that tangent line, okay? Remember, these are graphs of x to the power of n, and you'll see that if the slope is half, for example, then the function will be x to the power of half. And if the slope is 3, then the function will be x cubed. So that's a very interesting exercise. And then we'll move on with some questions involving calculations, right? So we'll have these 3 questions, right? Rather 4 questions. These will include thinking questions and application questions. So the first question is straightforward. It says, give an example of a function that is continuous but is not differentiable at x equals to 2, right? So you can get a couple of examples based on this. Then determine derivative, right, for f of x equals to x times absolute x. Justify your answer. Now, some students may say it does not exist, some may say it exists, but whatever it is, you have to justify your answer. Then we have another test question, which is from first principle, find the derivative of function 2x over 3x plus 5. Now, this is a difficult question using first principle, and it is seen in test papers. So all these questions are very important to review and do well in your test. The last question is an application which says an object moves in a straight line with its position at t equals to at time t seconds given by, this is a displacement function, s of t equals to 8t minus t squared, where s is measured in meters. Find the velocity when t equals to 0, t equals to 4, and t equals to 6. Now, using first principle, we have to come out with a general formula and then substitute the value of time 0, 4, and 6 and get the answer. So that is how you're going to do this particular question, right? So let's begin with our series. Now we will solve these questions, correct? So let me begin with this question itself, which is right there. It says, give an example of a function that is continuous but is not differentiable. Now, what do you mean by not differentiable? That is very important to understand. Whenever we are differentiating the functions, we are trying to find slope of a tangent line, right? So that is what it is most of the time. Now here what I will do is give you 3 examples. Okay. All 3 functions should be continuous, right? So look at this function. If I have a curve which is, this function is x to the power of 1 over 3. Now it's like a cube root function on this side. However, on this side is kind of like this. Now you will notice that at 0, if I draw a tangent line, it is going to be a vertical line. Do you see that? So it is a vertical line. Since it is a vertical line, we see that the slope of tangent is undefined. So if the slope of tangent is undefined, we say a function is not differentiable. So that could be one of your examples. I hope you are getting the point, correct? So if I have cube root of a function, then you'll get this kind of a graph where at 0 we have a vertical tangent line. So there is a tangent, right, which you can draw. However, the slope is undefined, and therefore we say it is not differentiable. Correct? Now let's take another continuous function, very famous, which is absolute function. So absolute function, well, I forgot. We have to do it at x equals to 2. This was at 0. So what I will do here is redraw. Translate it 2 units to... So now I've corrected. So good, I saw it, right? So it is x equals to 2. So at 2, it is not differentiable. So this function, I will call this as x minus 2 to the power of 1 over 3. Does make sense to you? Right. So that becomes our solution for the given question. So now I'll take a note on this, and now we'll draw an absolute function which is translated 2 units to the right. So that function for us is absolute value of x minus 2. So we can say y equals to absolute value of x minus 2. It is not differentiable here, since if I approach from the left side, I'm trying to get the tangent as negative 1. If I approach from the right side, I get a tangent which is positive 1. We are not sure which one is correct. So from both sides, if we get different slopes, then again we are not decided which one is the right one, correct? So we say if on a graph you see a corner, then we know that the slopes are different. If you approach from left and right, and therefore it is not differentiable. I hope that makes sense, right? Now another kind of function which you could draw and not differentiable could have a cusp here, right? So you could give any of these examples. So at 2, you could have a cusp as I've shown here, right? So a function which will be kind of like this will have radical power. I could write this function as f of x equals 2. Again, we have translated 2 units to the right. And so everything is positive, so it is 2 over 3. Do you see that? So that kind of a function. So if I square this cube root function, this is what I'm going to get. Do you see that? 2 over 3. So that cusp, remember, that cusp at a point makes it undifferentiable, right? So it cannot be differentiated at 2, since again, the asymptote here is, I should say not asymptote, the tangent is having a vertical slope, so it is undefined slope. So in this case, again, it is undefined slope of tangent. Correct? So that is a very good example. So these are 3 very good examples of functions which are continuous, but they are not differentiable at a given point. Perfect? Now, let me take up the examples which I began with. So I'll now take up a few more examples, and we'll calculate slope using tangent line. So now we'll get to our original questions. Now we'll explore how to find slope of a tangent line and relate it with the derivative of the function. In this particular exercise, we'll actually find slope of tangent line for all these functions which are represented by y equals to x to the power of n at the point 1, 1, right? So if x is 1, then anything to the power of 1 is going to be 1. That's the whole idea, right? So we have different kinds of functions here. To get the slope at a point, what we need to do is basically draw a tangent line, right? So at this point, I can draw a tangent line which could be like this. Do you see that? So let me just draw a tangent line. You have to do a neater job. I'm just showing you how to do it. And then what we see here is that we can now make a triangle, correct? So this is a good triangle which we have. And from this triangle, I can write slope m is change in y over change in x. So the change in y is from 1 to 3, which is 2, and change in x is from 1 to 2, which is 1. And therefore the slope is 2. You will notice that this particular graph is of y equals to x squared. And slope of that at the point which is 1, 1 is 2. Now let's get to the next one. Now here if I draw a tangent line, then what do I get? So I have to draw a tangent line here. So if you take a scale and then do it, it will be kind of like this, right? So here what you notice is this is not so accurate, but in any case, let me use a different thing. So if I draw this and rise over run, then what I notice here, actually this is not a very good graph. This is not tangent. So let me redo it. It's not a good graph. So it doesn't look like a tangent, right? So it is kind of weird. So let me draw another line here. Okay, so this is better estimate. Okay, so I'll continue with the same point, but the thing is this. So what you find is the tangent, this is better tangent than that, of course. The slope of this now is change in the y value, which is from 1 to 4, so which is 3, and from 1 to 2 it is 1. So in this particular case, we get slope as 3, right? 3 over 1. And you'll find that this graph is actually the graph of x cubed. Do you see that? So a power function slope at 1 is actually the power itself. That's very important to understand. Here, if I draw the tangent line, let's do it. So you get a line like this, correct? So that becomes the tangent line. Now, since it is dropping down, so the rise here, delta y over delta x, is minus 1 over 1, which is negative 1. Perfect? And in this particular case, this graph is actually of y equals to x to the power of minus 1 or 1 over x. Do you see that? So the power and tangent at this point is same. Perfect. Now here we have a graph where we'll again draw a tangent line. So what we have here is, so if I draw a line here, it is kind of going like, let me just draw. Okay, so that's the tangent line, correct? So now if I make a triangle, I get what? This is what I get, right? So in this particular triangle, I notice that change in y is 1 and change in x is 2, right? From 1 to 3. And therefore, in this case, the slope is 1 over 2. Since it is rising, it is positive. And the graph here is y equals to square root of x. Do you see that? X to the power of half. Perfect. Now, in this particular case, let me draw a tangent. So what we get here is kind of like this. Let me just go like this. Okay, this is good. Now, if that's the tangent line, the slope is negative 1. This is y, tangent y is negative 1. And the run is of 3, correct? So in this particular case, we get slope m equals to negative 1 over 3. And you will notice that this graph is of the function y equals to x to the power of minus 1 over 3 or 1 over cube root of x. Do you get an idea? Okay. Similarly, the last graph if you draw the tangent here, then you will get this function is y to the power of x2 over 3, right? So what should be the slope? Slope should be 2 over 3 at the point 1, 1. Do you see that? So draw the tangent and you'll figure out that when you draw the tangent, rise is of 2 and run is of 3, right? So if you do this tangent, then you'll get a line which is kind of like this. And if you form a triangle, then the run is of 3 and the rise is of 2. So you said delta y is 2 and delta x is equal to 3. And that is how from the tangent you get the slope. Now this is very important exercise, and you will soon learn in the next chapter that the derivative of y to the power x to the power of n, and we could write like this, y dash is n x to the power of n minus 1. So this n, when x is 1, is same as the exponent. And that's the reason why our slope for the tangent line approached the value of the exponent, right? So I hope that's a very interesting take from this particular video, and this will give you an idea about how the derivative's value should be for a given function, correct? So let's take one more example where we are talking about just looking at the graph of the function and then answering. Now this helps to understand the whole chapter, right? Now the question here is, identify the points where the function is not differentiable. So we have done this. It should be clear for you. So you should identify the points where the function is not differentiable. So let me mark those points. So here the function is not differentiable at this point, since it is a corner. From left seems to be a tangent of -1 slope. From right it is +1. Here this again is a cusp, not differentiable. Here a discontinuity. Here again a discontinuity, right? So those ones are very clear. So this is a corner, right? Here we have a cusp, correct? Here we have a discontinuity. Now, when there is a discontinuity, you don't know where to draw a tangent, correct? So you can't draw a discontinuity. You cannot draw a tangent here, right? So that is ambiguous, right? So it is not differentiable at this point. Here, it is a vertical asymptote. And the point x equals to -2 is not in domain. Do you understand? And therefore, the function is not differentiable at that point. The function is not differentiable because the point is not in domain. How can you draw a tangent line? But I want you to give me the reason for what I have left here. Why is this function not differentiable at ±4? So whenever we talk about differentiability, we're actually approaching from both the sides. It's very important to understand. So you have to find a limit of the function as you approach from the left side and from right side. Now in this case, you cannot approach from the left side, right? So therefore, it is not differentiable at + and -4. Do you understand? That is the reason, correct? So whenever you have a starting point of a function, then you can say it is differentiable in between, but not at 4 and ±4. So it is not differentiable at x equals to ±4, right? So because you cannot approach from the outside, that is the whole idea, right? And the blank space here is for you to sketch a function which is not differentiable at some point, right? Now to give you an example which is not here, I will use a function which is kind of like this, right? So if it is vertical here, kind of, do you see this? Now we do have a continuous function. It is not differentiable at x equals to 0 since we have a vertical tangent. correct? So if you have a vertical tangent, which is also the case here, in that case, the function is not differentiable. Perfect. So that is how you can answer these kinds of questions. So I hope now you can answer questions related to graph. Now let's look into more algebraic expressions where we are going to justify whether you can find a derivative or you cannot find a derivative, correct? So this is, now in this unit, it's just the beginning of the unit, we are still understanding the basic concepts about derivatives, right? The question here is, determine the derivative of f of x for f of x equals to x times absolute x. Justify your answer. So we'll use the basic definition of derivatives to get the result, right? So we say that the derivative of a function f of x in general is limit when x, I should write, we're not taking a particular point, in general, when h approaches 0 for f of x plus h minus f of x over, it's kind of rate of change. So normally we write x plus h minus x, right? Now which could be written as limit h approaches 0 for f of x plus h minus f of x over h. As you can see, we have to approach 0 from both the sides for the limit to exist, and if the limit exists, then the function is differentiable. So that is the basic, right? Now in our case, we are given a function which is equals to x times absolute value of x, right? How do you find its derivative? So what we will do here is that we are going to approach 0 from both the sides, correct? So if let's say first one, we say limit of this function when approaching from the left side, that means left side. Is that okay? So when I approach from the left side, I have a value which is 0 minus x, correct? Correct? So I have a value. So normally we write x plus h, but when we approach from left side and the value is 0, how should I write it? I should write this as f of 0 minus h. So that means approaching from the left side. You get the idea. So x is 0 minus h for us, minus f of 0 over h. Do you see that? But when we approach the function from the right side, then it becomes limit h approaches 0 from the right side, then it is f of 0 plus h. So you're on the right side of origin, minus f of 0. Does make sense to you? Now, x plus h, let me write like this. So this is 0 minus h minus 0. And here it will be 0 plus h minus 0. Do you see that? So I'd like you to take a moment and understand what we have done. So we are moving from this place. We want to find whether this function is differentiable at origin or not, right? So determine if this function, actually the question is missing, determine f dash x for this function, correct? We have to do that. Okay. Now, at x equals to 0 is missing here actually, because otherwise it is a continuous function and we can easily find its derivative, but at x equals to 0 there is confusion, so we'll just work that out. Okay, so now at x equals to 0 you could approach from left side or from the right side. So if you are approaching from the left side, then the point is 0 minus h, correct? So that becomes the expression for the limit. Approaching from the right side, it is 0 plus h, and that is your expression. Perfect. Now let's write down this expression here. We get limit h approaches 0 from the left side, and I'm replacing x with 0 minus h. So what I get here is 0 minus h times absolute value of 0 minus h. Is it okay? Okay, I wrote like this. minus f of 0. So f of 0 we know is 0. Okay, divided by, when I say 0 minus h minus 0, we get minus h here. Perfect. Now we have limit h approaches 0 from the left side. 0 minus h is negative h. Absolute value of minus h is positive h. Perfect. Divide by minus h. Right? So this minus and minus cancels. So we get a value h. Is it okay? So we get a value h. And substituting 0, we get 0. Correct? On the other hand, if I do this, then the derivative of this function is limit h approaches 0 from the right side. Substituting 0 plus h gives me 0 plus h for x, then absolute value of 0 plus h minus 0 over 0 plus h minus 0 is h. Is that okay? So that gives you limit h approaches 0 from the right side. This is h, absolute value of h, which is also positive h, and we get positive h. Correct? So, I should write limit h approaches 0, which is 0 for us. So both the values are 0. Since the limit exists from both the sides and is same, so we say the function is differentiable at x equals to 0. Do you get an idea? Correct? So that is how we show that this function x times absolute x is differentiable at x equals to 0, and the slope of the tangent at this point is 0, right? So if you sketch this function, let me sketch it here. If you sketch it, it is like a parabola on this side, correct? And minus of this reflected kind of like this on this side. So the tangent line is horizontal at x equals to 0. It is differentiable at x equals to 0 as shown in this particular video. I hope that makes sense. Thank you. Now let us find the derivative of the function using first principle. The function given to us is f of x equals to 2x over 3x plus 5. In later chapters, we'll learn some rules like power rule, product rule, quotient rule. It'll be very easy to find derivatives. But at present, to find derivative, we are going to use the first principle, which is we'll find limit as h approaches 0 for f of x plus h minus f of x over h. So that's the whole idea, right? So we are going to replace x with x plus h. So what we get here is limit h approaches 0. This is h, okay. Approaches 0. F of x plus h means we'll replace this x with x plus h. So we get 2 times x plus h over 3 times x plus h plus 5 minus the function, which is 2x over 3x plus 5 and everything divided by h. So what we get here, so everything divided by h, this is what we have. Now we'll take common denominator, right? So we have limit h approaches 0. So if I take common denominator, we have 2 also common. So let me write down 2 over h as a common factor. Is that okay? So 2 I'm factoring out. I'm writing h outside. Is that okay? So it becomes simpler. So the common denominator is 3 times x plus h plus 5 times 3x plus 5, correct? And now we'll cross multiply. So we have x plus h times 3x plus 5 minus 2 I've already factored out. So x times all this. 3 times x plus h plus 5. So that is what you get, right? Now we can just open this up and simplify. So we have limit h approaches 0, 2 over h. So if I multiply, you get 3x squared plus 5x plus 3xh plus 5h, right? So 4 terms. And here we'll multiply with x all these terms. So we get minus, all will be negative, minus 3x squared. Then we have got minus 3xh. Now that's done with 3. With 5 we have to multiply minus x, so minus 5x divided by product of these two. So it is 3 times x plus h plus 5. The other term is 3x plus 5. So in the numerator, these 3 terms have to cancel. So 5x and 5x, 3xh, 3xh, and 3x squared and 3x squared, right? Otherwise there is a mistake. Then we have limit h approaches 0, 2 over h. What remains is 5h, that's all, over, we have 2 over h here, and over all this, okay. So let me write all this. 3 times, okay, x plus h plus 5 times 3x plus 5, okay. Now, we can cancel these h from numerator and denominator, and then we can substitute h equals to 0. Is that okay? So what we get here is limit h approaches 0. We have 5 times 2 as 10. Is it okay? 10 over all this. Now, let me write this first. So we have 3 times x plus h plus 5 as first factor. The second one is 3x plus 5. Now we could substitute h equals to 0 and we get 10 over 3x plus 5 times 3x plus 5, or we will write this as 10 over 3x plus 5 whole square. So this becomes the derivative of the given function. Do you see that? So using first principle, you may have to do a lot of work. However, you get your answer, and that's how you do it. Later in section 2.4 or 5, we can do it using product rule and quotient rule and get this answer very fast. So let's continue with more examples. Here's the last example from our series on 2.1 review. The question here is, an object moves in a straight line with its position at time t seconds given by s of t equals to 8t minus t squared, where s is measured in meters. Find the velocity when t equals to 0, t equals to 4, and t equals to 6. You can always pause the video, answer this question, and then look into my suggestions. So whenever we have to find derivative, velocity's derivative of displacement at many points, it is good practice to start with a general solution, right? So what we're given here is displacement s of t is 8t minus t squared. Now, as you know, velocity is actually rate of change of displacement, right? It is rate of change of displacement with time, right? So we'll find the derivative of this function. Now we are going to find the derivative of this function using basic concepts of limits. So we'll say limit h approaches 0, and we'll say s of t plus h minus s of t over h. So that is how we are going to find the rate of change, which is velocity. So we can write this as the derivative of displacement is limit h approaches 0, and we'll replace t with t plus h. So we have 8 times t plus h minus t plus h whole square over h. Okay, I'm sorry, this is the first function. Okay, this is st plus h, and from here we'll take away st. Is that okay? Right. So which is minus of 8t minus t square. Perfect. So that gives you limit h approaches 0. So let's expand this. So we have 8t plus 8h minus, all terms with negative, t square minus 2th minus h square. And let's open this also. We get minus 8t plus t square over h. Correct? Now these two terms should cancel. Otherwise, there is a mistake. Okay? Remember that part. So we have limit h approaches 0. All terms are with h. Do you see that? We got 8h minus 2th minus h square over h. So that gives us limit h approaches 0. We can take h common. So we get 8 minus 2t minus h over h. So once they cancel away, you can substitute 0 and you get 8 minus 2t. So basically the derivative is 8 minus 2t. So now we can write that the velocity at any instance of time is same as the derivative, and it is same as 8 minus 2t. Correct? We need to find velocity at t equals to 0. So we'll say velocity at 0 is, substitute 0 for t, right? It is 8 minus 2 times 0, which is 8. Then we have velocity at 4. So we get 8 minus 2 times 4, which is 0, right? And of course, the units will be all meters per second, right? So meters per second. So all units are meters per second. And the last one is t equals to 6. So write velocity at 6 is 8 minus 2 times 6, which is 12. So we get minus 4 meters per second, right? So all units are in meters per second. So it is 8 meters per second. So we get the velocity of the function at different instance of time after finding a general expression. So that becomes a general expression. Substitute t to all different values and get your answer, right? So I hope with this you understand fairly well how to work with derivatives. What are derivatives? When is a function differentiable? When it is not differentiable? Why it is not differentiable? And how to use first difference quotient, the limits which we learned about those concepts to find derivatives, right? And in the next unit, we'll see how to calculate derivatives very fast using the formula for power rule, then scalar times power rule, product rule, and quotient rule. Thanks for watching and your time. Hope it helps. Thanks and all the best.